Hey everyone, I'm Nick, and welcome to Foundations of Computer Architecture. So this series is going to be a first course in computer architecture, where I'll be including some of my own personal insights from academic research to industry along the way. So to get started, as a little bit of background about myself, I'm Nick. I'm a performance engineer and computer architect. I work for a deep learning accelerator startup, and most of my background is in GPU architecture, simulation, and modeling. In my spare time, I do a lot of teaching. So I'll write things like blog posts on high-performance programming, performance optimization, and tuning. I do video tutorials on similar subjects, and I've done a number of in-person tutorials in the past as well. So what exactly are we going to cover in this series? So we're going to try to answer these 4 key questions about computer architecture. So starting out, we're going to try to answer the question of how do computers execute programs? And this is going to lead us into a discussion on the language of processors, which is instructions in the processor's instruction set. And also, how do processors actually compute things? And how do they perform arithmetic on things like floating point numbers and integer numbers that are represented at the lowest level in binary? Next, we're going to try to answer the question of how is the core of a CPU organized? And how do we design something like a data path? So, we know we have these instructions that we want to execute, but what kind of hardware structures do we need in order to facilitate this? And how do we handle things like hazards and dependencies between instructions? Next, we're going to try to answer the question of how do we interact with memory? So all of our data and our instructions are sitting off in memory someplace. So how do we actually access that memory? And very importantly, how do we organize that memory? And this is going to lead us into a discussion of the memory hierarchy and the different trade-offs we have in terms of cost, size, and performance. We'll also be touching on some other very important topics related to memory, like virtual memory and cache coherence. And then finally, we're going to talk about how do we scale computers. In answering this question, this is going to bring up things like parallel architectures, like multi-core CPUs, as well as dedicated accelerators, things like GPUs. So what is this course going to be based on, right, in this series? So this series is going to be based upon the classic book used for a first course in computer architecture, which is Computer Organization and Design, the Hardware-Software Interface, sometimes referred to as the Patterson and Hennessy book. And there are many different editions of this book for different ISAs, right? So there'll be a RISC-V edition, a MIPS edition, and an ARM edition. All of these cover roughly the same thing in terms of computer architecture, the main difference, of course, being the specific ISA that gets used throughout the book. For this series, I'll be mainly using the RISC-V edition, and I would suggest if you were planning on looking through one of these books or picking one up for yourself, to maybe look at getting the RISC-V or the ARM edition, namely because these are 2 ISAs that are incredibly popular today. So let's go ahead and get started. And to start out, we'll do a brief discussion, just kind of the landscape of computing today. So computers really come in all shapes and sizes. We have computers that are as small as a stick of gum, and computers that are enormous, like the size of a warehouse. So on the small end of things, you can have something like a Raspberry Pi or a Raspberry Pi Zero. And the large side of things, you have, giant supercomputers like the Summit supercomputer that I believe was at Oak Ridge National Lab. That'll take up an entire warehouse. You'll also find that computers are pretty much everywhere today. So we have computers in our cars, controlling not just the electronics, but also things like the braking and the engine and even the steering. We carry computers around with us almost every day in the form of cell phones or laptops. We, of course, have our personal computers, and over the past few decades, we've become surrounded with these IoT devices, these Internet of Things devices like smart thermostats and smart light bulbs and smart doorbells. So computers really affect every part of our lives now. You'll also find that computers are built for very different tasks. So we have computers that are very general purpose. So something like your laptop or your personal computer that's designed to run a wide variety of applications, from browsers to video games to word processors. But we'll also design computers for very specific tasks. So they may only be good for a small subset of tasks or one very particular task. So maybe that's machine learning training or machine learning inference. So kind of the key takeaway from this is that we design computers for different ways depending on what we're using them for. So the design decisions we'd make for Raspberry Pi are going to be very different than the ones that we'd make for a giant supercomputer like Summit. And likewise, computers that we're going to be placing inside of our car will be very different than the ones we put inside of a laptop maybe, or inside of an IoT device, right? And there's all these different design criteria that we can think about in terms of performance, our power budget, how much memory do we need, what kind of processing power do we need. These are all very interesting things to think about in the context of what are we designing. So in the context of designing, the book lays out these 8 great ideas in computer architecture. And these 8 great ideas are really these core ideas that pop up over and over again over the decades in computer architecture research, and have been incredibly impactful on the community. And starting out, we have none other than number 1 on this list, which is designing for Moore's law. So many people are familiar with Moore's law, or have at least heard about it, or maybe that Moore's law is over or Moore's law is dead. So what exactly was it? So Moore's law was this economic trend that was true for decades, where every 1.5 to 2 years, we basically get double the amount of resources on an integrated circuit, and for a constant chip area, right? So we'd have, say, one size chip, and then 2 years later, we'd have, say, double the number of transistors on that chip. Now, the reason why people say that Moore's law is dead is because this is no longer true for a constant area chip. And this is namely due to technology scaling. So it's become increasingly difficult to scale transistors down, right? So going from, say, 90 nanometers down to 65 nanometers is much easier than going from, say, 10 nanometers down to 5 nanometers, or down to 3 nanometers, right? It's incredibly difficult to do. Now, while this is true that we don't get double the amount of resources on a constant chip area, Moore's law has continued in some sense in the fact that we're making increasingly larger processors. So if you look at this microprocessor trend data, you can see that, in this logarithmic scale on the y-axis, the transistors in thousands that we have on our chips is still increasing at roughly the same rate. We're just making larger chips. So what do all these things mean to designers, right? What does designing for Moore's law mean to a designer? It means we have to be very forward-thinking, right? We have to anticipate these technology advancements, be they, we're going to have double the amount of resources in 2 years. How are we going to build these larger chips? These are all things that we need to consider, right? And number 2 on the list, we have this idea of using abstraction to simplify design. So computers, as you're probably well aware, are incredibly complex things. And so we not only have these very complex cores, we have a very complex memory system. And these two things are going to interact with each other, which adds additional complexity. And this complexity only increases as we make larger and larger chips. We go from single core to multi-core to multi-node systems. So what does this mean for designers? It means we have to use the appropriate level of detail for the task at hand. So we need to make it in such a way where, an engineer doesn't need to know everything about every particular subsystem in order to do their job. We need to be able to design good interfaces and abstract things away, and only expose those low-level details as necessary. And this is true throughout the stack, from high-level application software to our system software, going all the way down to the hardware. And number 3 on the list, we have this idea of making the common case fast. And of course, we have none other than a picture of Jean Amdahl on the right, which is very famous for this idea of Amdahl's law, related to making the common case fast. So this boils down to the fact that not every situation is equally likely to occur. So a processor has many different instructions that it supports. Some of these instructions are rarely executed, right? So we may execute, a lot of multiplies and adds in almost every single program that we run. But we don't often execute something like an inverse square root, right? It's very uncommon. There may be applications that do inverse square root quite a lot, but the majority of applications are probably mainly going to be multiplies and adds. And likewise, there are some computation patterns that are incredibly uncommon. So it would be very common to access data, if we're talking about an array, we'll access element 0, then 1, then 2, then 3. We access data in order. But there may be incredibly complex access patterns, right, that are just very uncommon, right? Most of the time, we may be accessing data linearly. So what does this mean for designers? It means that we should spend time optimizing what will occur most frequently. And a great example of this is with general purpose processors versus application-specific accelerators. So what you can often think of an application-specific accelerator as is we take the common case that we're running on, say, a general-purpose processor, like a CPU, and we design something like an accelerator to specifically accelerate that common case running, right? So, if we're doing tons of matrix multiplication in something like a machine learning workload, instead of running it on a general purpose CPU, we can design an accelerator that's very good at, just matrix multiplication or matrix multiplication and a few other things, right? With this core idea of optimizing for the common case. And number 4 on the list, we have this idea of extracting performance via parallelism. So some work and applications can be done independently. So we can have independent operations within a single task. So, we may have multiple data operations. So an array of data that we're adding to another array. So each element that we're adding together is completely independent of each other. Or we may have just completely different tasks. So you might have, a video game open and a web browser open, right? Just completely different applications. So what does this mean for designers? It means that we design architectures to exploit this parallelism, which means that we design architectures that have vector instructions. So instructions that can compute multiple elements at the same time. So do, say, 8 multiplications at the same time, 8 additions at the same time. And we also design multi-core processors. So we have multiple different cores where different applications can be running at the same time. Next, we have this idea of performance via pipelining. So when we're executing instructions, one instruction doesn't need or doesn't require all of the processor's resources at once, right? Even if 2 instructions, that are back to back, have a dependency, they may have independent parts. So for example, if we're adding 2 numbers together and we're going to use that result in the next addition, right, there still might be independent parts of the execution of those 2 instructions. And a great example of this is something like an assembly line. So, we'll have, say, at the first stage of the assembly line, we're assembling maybe some sort of toy. The second stage, we're painting that toy. And the third stage, we're boxing that toy up, right? We're packaging that toy. Well, while someone's boxing up one toy, another person could be painting another toy, and the first person could, say, be assembling another toy. So we can overlap these operations together, and we can do the exact same things with instructions with pipelined processors. So what does this mean for designers? We design these pipeline architectures to exploit this overlap. At number 6, we have this idea of performance via prediction. So a lot of things we do, especially on CPUs, follows this idea of it's better to ask forgiveness than permission, which means we're not waiting around to execute things in many cases, especially with things like branch prediction. We'll just guess and then hope that we're right? And this works really well if incorrect guesses are fairly infrequent, or if we have a way to relatively inexpensively correct, right, if we guessed incorrectly. So what does this mean for designers? It means we design highly speculative processors. But this comes with a number of pitfalls, and I've got the ghost that's that was the image used for the exploit known as Spectre that was related to speculative execution. So there's a number of very important things related to prediction that have become increasingly important as things like Spectre have come out, which means that, coupled along with making these highly speculative processors, we often have to ensure things like invalid state. So when we misspeculate, it's never actually visible in any way, while we're also trying to minimize the penalty of misprediction. Right, so this performance via prediction, while it has a number of benefits, it can be very tricky to get right in terms of potential security pitfalls. And number 7, we have this idea of a hierarchy of memories. So ideally, we want a fast, large, and cheap memory. But it's really impossible to have all three. Right? We can have a fast and large memory, but it's certainly not going to be cheap. And we can have a large and cheap memory, but it's certainly not going to be fast. But oftentimes we don't need something to be fast, large, and cheap. We can often get away with having a compromise through a hierarchy, right? So what does this mean for designers? It means that we often carefully size the different types of memory we have to give the illusion that we have fast, large, and cheap memory. We also have to very carefully design how they interact, right? And this is something we'll really dig into in the memory section of this series. And number 8 on the list, and our final bullet on this list of 8 great ideas, is this idea of dependability via redundancy. So computers need to be more than fast, right? They need to be dependable. If we have a computer that is incredibly fast but crashes all the time, well, it's not going to be very useful. And it's especially important in a number of circumstances. So with something like a personal computer, if you get an error, maybe you get the dreaded Windows blue screen, right? Okay, you have to restart your computer. Not a terribly big deal. Maybe a bit annoying, maybe you lose some work, but not the end of the world. Well, what happens if the computer on your satellite crashes? Suddenly, this idea of dependency and reliability becomes much more important. It's very difficult to do a quick replacement on a piece of hardware on a satellite than it is to, say, on your laptop. So what does this mean for designers? It means we need to design ways in hardware in order to catch errors. And if possible, we need to be able to design ways to recover from errors when they occur. So now that we've covered a lot of these great ideas in computer architecture and the different ways that we do design, we can start talking about how software and hardware really interact. So software and hardware work together in layers, right? So we have these layers of abstraction. So oftentimes we can break these out into 3 layers, right? We have our application software, which sits at the outer surface. One level deeper, we have our system software, and then below that we have our hardware. So our application software will be just, an application that we'll write. So something like a Hello World program. Between that and the hardware, we have our system software, which includes things like operating systems and compilers. So instead of writing, say, a high-level program that has to do all the things related to process scheduling and memory management of the actual hardware, right? We rely on system software for these things. We abstract those things away to the system software. And then we, of course, have hardware where all of our applications are actually running at the end of the day. So your system software is acting like a middleman, and this nice layer of abstraction where somebody writing application software doesn't need to worry about all the small details related to hardware. So, on this line of how programs actually execute, we have this core idea that computers don't actually understand C or C++ or high-level languages in general. What a processor understands is instructions. And very specifically, they understand these instructions that are encoded as bits inside of an executable. So we have patterns of bits that the processor understands at the hardware level. It decodes it to have a certain meaning. Maybe this pattern of bits means to add these two registers together or multiply them together, right? Or maybe read something from memory. And we use the system software like compilers to translate from one language to another. So as an example, we'll use a compiler to translate our high-level C++ programs into the x86 instructions in the form of an executable that will actually run on our processor. Now this brings up perhaps the obvious idea of why not write everything in assembly, right? If that's what's getting translated directly into ones and zeros and then running on the processor, why not just do everything in assembly? And the two main motivations for not doing this is namely productivity and portability. So assembly instructions tend to be very, very simple, right? And not very expressive. So doing something very complicated can take thousands, tens of thousands, hundreds of thousands of instructions, right? Something that's incredibly difficult to do, and they can do a lot faster using a more expressive high-level language. Likewise, there's this idea of portability. So not every instruction works on every processor, right? So we have different instruction sets. So x86 instructions don't work on an ARM processor. And the same goes vice versa. ARM instructions don't work on an x86 processor. And even between generations of processors, say between x86 processors, certain instructions, don't exist, right? If you go, back to earlier generations of x86 processors, there may be certain SIMD extensions that don't exist. So when we write things in high-level languages and have these nice pieces of system software like compilers, we don't have to worry about this as much in terms of portability. We can write our high-level code in C or C++ once, and then compile it for many different targets and just rely on the compiler to do this translation for us. So we pay the one-time cost, or, it's going to be developed over the years, of course, with the compiler, but we pay the relatively small cost of investing in a good compiler. And then we don't have to write 10 different versions of our applications for 10 different processors. That being said, though, many pieces of software are still written in assembly, namely very, very performance-critical pieces of software, right? So things like linear algebra kernels, right, that are the core of certain applications, or very highly optimized routines like spin locks will often be written directly in assembly, right? Because performance is incredibly critical with those things. So to kind of explain how this translation goes through with something like a compiler, we have kind of a simple flow for a Hello World program and how things look kind of at each step. So starting out, we of course have our high-level source code written in C++. So something like helloworld.cpp. And this is something that we'll pass to our compiler driver. So something like G++, where a compiler driver is just it's just another application that knows how to invoke all the different parts of the compiler. So these will be things like the preprocessor, the compiler, the assembler, and the linker. So the actual compiler is just one process of generating the executable. So what we'll do is we'll hand our high-level source code to the compiler driver, and we'll first do things like preprocessing and compilation. So we'll translate our high-level C++ into the instructions of the processor that we can read, right? So we'll end up with something like this hello world.s, right? So our x86 instructions, dumped out into this file that we can dump out if we want to. After we have this, right, our instructions, we then pass it on to the assembler and the linker. So the assembler will take these x86 instructions and translate them into object code or machine code. So it turns it into the ones and zeros that the processor can understand. And the linker's there to tie up all the different pieces of source code we have into one executable. right? And then we end up with our hello world.out, or whatever we want to call our executable. And this is what we actually end up running and executing on the processor. So as you can see here, just generating an executable for something as simple as hello world involves a coordination of many different things. So not only do we have a high-level language that's completely designed like C++, we also have all of these tools like our compiler driver, our preprocessor, the compiler itself, the assembler, the linker. This isn't even getting into the operating system and the loader, right? All of these different things that are working together just to execute something like hello world, right? And all of the programs that we end up running. So that's going to go ahead and do it for this video. There's a few closing thoughts. Computers are used almost everywhere, come in all shapes and sizes, and we design them in different ways. And how we design them often comes down to a number of these core design principles and these 8 great ideas in computer architecture. We saw how hardware and software interact through this hierarchy of layers, from application software to system software, down to the hardware itself. And we saw how many moving parts actually need to come together to go from high-level source code to actually executing something that's going to run on the hardware. So that's going to go ahead and do it for this video. As always, stay tuned for more computer architecture videos. We'll have some more advanced architecture videos coming up, videos on some special topics in architecture, like memory consistency and cache coherence. And I'll also have some videos answering some questions related to all of these architecture videos coming out as well. Feel free to check out any of my open source blogs, code, or books on my GitHub page at github.com/coffeebeforearch. I host a lot of my stuff also on the group that I created called Open Arch Group on GitHub. And of course, I have my GitHub page website where I host all my blog posts at coffeebeforearch.github.io. That's going to go ahead and do it for today. As always, I'm Nick, and I hope you had a nice day.